Okay, welcome to National Mickey Mouse Day, and we thought we'd start off with a couple jokes. Why did Mickey Mouse get plastered with a snowball? Well, that was because Donald Duck ducked. And then the second one is, why did Mickey Mouse go out to space? To find his buddy Pluto. Isn't that nice? So, let's get started on today's lesson. It is on inverse functions, and we're going to start with algebraic inverse functions and then get to trig inverse functions. And these do get a little bit complicated. This is the last section of the chapter, and so this will explain, inverse functions for trig will explain why your calculator gives you certain angles when you plug in inverse functions. Some were positive, some were negative, some were obtuse angles, and there's a reason behind that. So the first thing that we want to know is, what is a function? Because we're talking about inverse trig functions. And a function is where each x has exactly one y. And a relation is any set of ordered pairs. The domain, as we talked before, is inputs or x's, range are outputs or y's, and then you have a vertical line test. Just a couple of points here. If I had a graph of a line, and that graph looked like this, and the question is that a function or is it not? This graph would represent a function, because if I took a vertical line and moved it in either direction, you would see that that vertical line only intersects the graph in exactly one place. There's only one y for each particular x. So this would be considered a function as well as relation. However, if I had a graph over here and it looked like this, this would fail the vertical line test because it would intersect it in two places, and therefore this would be not a function, but it would be a relation. Why? Because at this x, it has two y's. Secondly, how do you get an inverse? And so when you get an inverse, you're actually switching your x and y's around. It's kind of like playing a cat and mouse game where you're switching the chase on them. And so you're switching the x's and the y's, and then you're representing the new y. So when you do this, you can label the inverse trig function in two ways. You can label it as arcsine of x, and these are some books will put it in this way or the other way. This one does it in both. And you can also do it as this notation, sine -1 x. And that -1 is not a power. It is not a -1 power. It is representing an inverse function. So this means inverse function. It does not mean power of -1. Just keep that clear. We're going to start with some easy algebra problems, and then we're going to get into graphing two trig inverses. And generally, students have a hard time with this, so you have to just keep things nice and clear as you go through it. Let's go ahead and look at some algebra problems, and it's just an algorithm that you have to follow, and the algorithm says change the x and the y and solve for your new y. Change the x and the y and solve for the new y. Number 1 says find the inverse of f of x equals 2x minus 3. F of x means it's actually a function. It's the function of x is equal to 2x minus 3. It's doing something to your x, and they're calling it f of x. So you're multiplying it by 2 and subtracting 3, and that's the function of x. And so if I want to make the inverse of this, what happens? Well, I replace it with a y, first of all, your f of x notation, and then I switch the two. And so these two are equal, but now all of a sudden when you switch, those are not equal anymore. I'm talking about my inverse. This now starts my inverse. And when you solve for y, you add 3 and divide by 2, you're going to get x plus 3 divided by 2 for your inverse function. And it is an inverse function because it's a line. And so your f inverse, your inverse function is equal to x plus 3 divided by 2. The notation says that it is actually an inverse function. And that's what I'm showing there. All right, pretty straightforward. You know the system. And so we're going to do one more and see what this looks like on a graph as well. So when I do this, it's really y equals x squared plus 1. And then I want to switch the x and the y to make the inverse. I don't know if it's a function yet, but I do know it's an inverse. So right now, when I switch it, it's going to be x equals y squared plus 1. And if I were to solve that for my new y, I would get y is equal to x minus 1 square root plus or minus. Just skipping a couple steps there. Now, so this is the inverse to that one. But the question is what's happening on the graph when you do the inverse? And this is important in getting into the trig functions. So when I graph this, the first graph looks like this because it's a parabola and shifted up 1. And this point is going to be at 0, 1. Well, what's happening is I'm taking every point on that parabola and I'm switching the x and y around, and that's going to be plotted on my inverse graph. So if I were to just put some points here, this is x, and then I want to do x squared plus 1. This is just my f of x here I'm talking about. And so if I put 0, I know I'm going to get 1. If I put 1, I know I'm going to get 2. If I put negative 1, I know I'm going to get 2. Negative 1 times negative 1 makes a positive 1. And so I know those points are going to be on here. Well, when I switch those around to get me the inverse, I now am going to have a point, 1, 0, which is right here, that's on my inverse graph. My next point is, I'll just write them out here, 1, 0, 2, 1, 2, negative 1 when I switch them, switching the x and the y. So my next one is 2, 1, and 2, negative 1. Notice what's happening. I'm taking these 3 points and I'm now moving them over here when I switch them. And so this graph is going to look like this, a parabola opening up this way. One of the key features of inverse functions actually is that it's reflexive about the x equals y line. It is going to reflect over the x equals y line. any inverse functions. This red line, this red graph, is not a function, however, because it fails the vertical line test. And so I can't write that as f inverse x because it is not an inverse function. So this red would be written just like this, y equals plus or minus the square root of x minus 1. A good question is, can I figure that out without graphing it? Can I figure out that it actually is an inverse and not an inverse function by just looking at this equation? And the answer is yes, because of this plus or minus. If you put a 5 in here for x, you would see that you're going to end up with plus or minus 2. And when you have plus or minus 2, you're going to see that 5 yields 2 y's. 5 is going to give you 2 y's when you plug that in. And therefore, each x would have 2 y's, not a function. All right, well, how does this relate to relations? Well, I want to graph two inverse functions. One, I'm actually going to do 4 things. I'm going to start with f of x equals cosine x, graph the inverse of the cosine x, and then I'm going to graph the inverse function of the cosine x. And then I'm going to do the same thing for the tangent. And that will wrap up what we're going to look at today. Some of these questions are homework questions. Draw the inverse function of the cosine x. We are breaking this down into 2 days. First day is going to be focusing on inverses, drawing them, figuring out what they are. And then the second one is going to be on what are we going to do with them. So we remember the cosine graph, and the cosine graph has points in it. So I'm just going to label these points. And I want to take those points and actually switch them to make the inverse. And so when I do that, I'm going to look at a new graph. And so this is going to be x is equal to cosine y graph. I switched the x and the y around. I can't do that on my graphing calculator because I can't just put x equals. Graphing calculator is always y equals. But I can do this by switching the points, x and y. So if I look at this first point, which is 0, 1, I now want to put on the new graph 1, 0, which means I'm going to have a point right here. I then go to this graph, and I'm looking at pi over 2, 0, which now becomes 0 pi over 2. Go back to this graph. Pi negative 1 becomes negative 1 pi. Three pi over 2, 0 becomes 0, 3 pi over 2. Two pi 0 becomes 0 pi over 2. Let me think about that. What happened here? Oh, sorry, this is mislabeled. This should be here. 2 pi goes to 1. Okay, now it makes more sense. 2 pi 1 becomes 1, 2 pi, which means that one's going to be up here somewhere. Now, if I connected those dots, this would look something like this. And if I were to continue that pattern, I'd have a negative pi over 2, negative pi, negative 3 pi over 2. And I'm just going to continue to mark those dots down, and then I can draw that in. Well, what's actually happening in this graph? It's going to go up and down to positive infinity and negative infinity because I switched with x's and y's. But we know that this is actually not a function, because if you put any vertical line in between 1 and negative 1, you're going to see there's an infinite number of y's. You only can have one on a function. So in order to make this a function, we have to actually limit, we have to make a cutoff of this inverse such that for each x has exactly one y. And so you've got to figure out where is that cutoff going to be. Well, you want to put it around 0 somewhere. And you could almost think that these were your quadrants: first quadrant, second quadrant, third quadrant, fourth quadrant. And so if I want to draw a function here, I'm going to be looking at where it does not repeat. And so if I start here and go to here, you're going to see that red line is going to indicate your f inverse of x line, which is the cosine inverse of x. Why is that true? Because each x has exactly one y. And you may remember when we used our graphing calculators to get inverse cosines and just plug numbers in to get angles. You may remember that the angles went from 0 to 180 degrees. You had obtuse angles that it was giving you. The reason why that's true is because this inverse function is defined from 0 to pi, or 0 to 180. So that's why it's giving you all angles within here. It never gave you a negative angle for the inverse cosine. It did for sine, but it didn't for cosine. It's only because it's defined from 0 to pi for the function. Let's take a look at the tangent. Putting in some points here. We're going to do the same thing. We're going to actually look and see what the tangent inverse is, and then what the tangent inverse function is by limiting the tangent. All right, by looking at this, you're going to see that asymptotes are the way that we framed out the tangent function at the beginning. Now we're going to be framing the inverse by doing the same thing, looking at the asymptotes. And so we're going to make an observation on this tangent graph that the asymptotes are all lined up with your x's. Well, for inverses, I want to line up my asymptotes with my y's. So I'm going to take those numbers on the x's and move them on the y's. To do that, I'm going to be looking at my asymptotes, which are going to go this way now. And I want to mark them in. So it's going to be pi over 2, negative pi over 2, negative 3 pi over 2. They go every pi unit. So I've got an idea of what my asymptotes are. The graph are not going to cross those lines. And then what I really need here is one point to get me started on this. And so if I take a look at this point, tangent of pi over 4 is equal to 1. I now can choose one point, which is going to be 1 pi over 4 now. 1 pi over 4, which means it's going to start. I know that that point is going to be on the graph. That's the only point that I really need to graph this. So I know that this inverse tangent is now going to look like this. And the pattern is going to continue. Tangents are more pattern oriented. We don't want to get into all the specific numbers. Asymptotes what we're looking at. Well, that's good, but I see that it's going to fail the vertical line test again because each x is going to have a certain y. So I have to limit it to each x being 1y. How do I limit this? I am going to create the inverse function. How do I create it? It's going to be this right here is going to represent the inverse tangent function. Each x has 1y. Notice what happens. You're talking about angles, your y angles, that are between negative pi over 2 and positive pi over 2. That's why when you use tangent inverse in your calculator, it's going to output only angles between 0 and pi over 2 and 0 and negative pi over 2. You're going to get negative angles when you use the tangent. It's because it's the way the function is defined is the way that that's programmed in. Or else they could give you an infinite number of angles. We went over, this is the last section, so we went over how to figure out how to do an inverse from just algebraic equations. We then looked at the cosine and the tangent graphs and found out the inverses of those, and then we talked about what the inverse functions of those would be, why we have to limit it. We want to make sure that we understand domains and ranges as well as these, for these. So the last thing is domain and range. On this tangent, domain would be all real numbers. The range, interesting enough now, is going to be y's not equal to, so it's going to go from negative pi over 2 to a positive pi over 2. Not including those endpoints. Domain and ranges. And for the cosine, we're looking at domain and ranges for this one. The domain are my x's. It's going to be all x's between and including negative 1 and 1. The range are going to be all y's that are going to be between and including 0 and pi. Looking at your y's and looking at your x's. All right, there's a lot going on. There's just a little bit more new material, which we'll get into tomorrow. But keep working on those story problems, setting them up. They're going to be due Friday. Do not procrastinate on those. Those are hard problems.